we should shift to the presentation by David Kring. David, are you okay? Ready to go?
Merci, Patrick. Can you see my slides?
Very well. Just go to full screen mode. Okay, perfect. And we hear you well.
Thank you very much. Okay, so I want to jump to this first picture of the Artemis exploration zone, which I hope everybody understands is defined as a region within 6 degrees of the lunar South Pole. All of the triangles that you see on this map are locations where we have conducted landing site and traverse analyses. Many of these are published in the papers that I have listed there, and a couple have been done by some of our colleagues in the international community, and I list 2 of them on that page. Today, I want to take a closer look at potential Artemis landing sites between the South Pole and Site 001, which is in the immediate vicinity of Shackleton Crater, and a ridge that extends from Shackleton Crater towards Henson Crater or Daguerreotypes Crater. I want to focus on the physical properties of the regolith that may affect robotic and crew traverses, such as trafficability, the power needed for robots, and the metabolic load that may be required of crew. Now, the physical properties of the polar regolith is an issue that we have been wrestling with for several years. Some investigators suggested the polar regolith, particularly within permanently shadowed regions, is significantly different than that experienced by Apollo and Luna landing sites. It was argued that the regolith is so porous that vehicles and later crew would sink into that regolith. This was such a serious issue that Survey sponsored a special workshop to discuss that issue in 2015. There was at that meeting, however, no resolution to the issues, which prompted a series of investigations. The first one was led by Valentin, the co-chair of today's mission, and we utilized a method that was demonstrated first during Apollo. That is, we used boulder tracks to assess the bearing capacity of regolith in different terrains. The augmented method was developed in sunlit pyroclastic deposits, which is a very attractive ISRU target. And then once that method had been demonstrated in the sunlit region, it was then applied to permanently shadowed regions, where in parallel, a new image processing technique needed to be developed to peer into those shadowed regions. And here's a very dramatic photo. This is from a paper by Hannah Sargent and others that shows a boulder track in the upper panel in sunlit region, seemingly to disappear in the PSR. And then once image processing techniques were utilized, basically looking at secondary illumination, to see the floor of that PSR, you can see that that boulder track continued uninterrupted and unchanged into the PSR. That actually suggested that the regolith of PSRs is not that different from the sunlit regions. There are some caveats, though, with that finding, and so I do refer you to Hannah's paper for that discussion. So using those methods, Valentin and I produced maps of the Artemis exploration zone, which you can see here, of bearing capacities. And you can see the values there range from less than 2 kilopascals to more than 13 kilopascals. Today, I want to update that published finding with a more detailed examination of the data in the immediate vicinity of the South Pole, which you see here in this wonderful oblique view of that region by Valentin, showing the South Pole, that's the SP, potential landing site 004 on the rim of Shackleton, and potential landing site 001 on that ridge that was cross-cut by Shackleton Crater between Shackleton Crater and Henson Crater. So here is the more detailed map of that region. You can see Shackleton Crater off to the upper right, Henson Crater is to the lower left, and Sputus Crater is to the on the near side in the upper left part of the diagram. This map of bearing capacity as a function of topography illustrates that the bearing capacities are relatively safe, except on those areas where there is significant slope. I should point out that the bearing capacity within PSRs, which are those black regions, may vary from the values shown here due to the potential influence of ice. And I again refer you to Hannah Sargent's paper for a detailed discussion of that point. The values, again, are scaled from less than 2 kilopascals to more than 13 kilopascals. For reference, values of 7 to 8, and I see I have a unit problem there, but 7 to 8 kilopascals were preferred for Apollo, and wheeled vehicles with ground pressures of 7 to 10 kilopascals were recommended for future missions based on that Apollo and Luna experience. Those results suggest that bearing capacities are sufficient for exploration along the rim of Shackleton Crater and the ridge that extends from Shackleton Crater towards Henson and Derlock craters. However, a major slope towards Sputus Crater, that is above Site 001, as shown in this illustration, may have significantly lower bearing capacity. Also, the walls of craters that crew would need to skirt along the top of that ridge may have significant lower bearing capacities. This is portraying that information in a slightly different format, basically is in a hazard notation. So this map illustrates areas of increased sinkage due to slopes steeper than 15 degrees, those are in orange, and slopes steeper than 25 degrees, and those areas are in red. It's important to note, however, when looking at this map, and if you try to use this map, that data scatter and historical experience suggests that there may be variable sinkage around the values shown here. Okay, we've worked very hard on this issue, as you can see, publishing a number of papers, but you know, as a lunar surface geologist, I have to say that we absolutely have to verify these values with in situ lunar surface measurements. And so to verify this type of map, we want to illustrate how you can do that in the vicinity of landing site at Site 001. So you could test these values in situ by looking at lander and footstep penetration, the stability of trench walls, cone penetrometer measurements, and vane shear device measurements, all of which can be applied in the immediate vicinity of the landing site, which you can see I've illustrated here with ELS. Also shown is a circle, which represents the 2-kilometer walking EVA limit currently envisioned for Artemis astronauts. So to illustrate an in situ test sequence, I have identified several sites within that zone, A through E. Location A would provide a measure of regolith in an area with a relatively high estimated bearing capacity. B represents an area with a relatively low estimate bearing capacity, so we bracket the range that we mapped. Location C represents an area within a permanently shadowed region. Location D has an estimated bearing capacity similar to that of A, but might be a necessary secondary test if location A appears to have been disturbed by rocket thrust from the lander at LS. Location E has an estimated bearing capacity similar to that of B, but is on a near side facing and earth facing slope that should be evaluated for potential differences. And as already noted, the properties of regolith will affect crew EVA and the trafficability of mobile surface assets. Those properties may also affect the recovery and extraction of volatiles from the regolith. So testing or verifying the values that we've mapped is very important. And these values will also affect the manipulation of regolith for shielding and other constructional purpose. Thus, these in situ measurements proposed will help address at least a half dozen of NASA's strategic knowledge gaps, or SKGs. And let me walk you through those now. So cone penetrometer and vane shear measurements at these sites, when combined with analyses of boulder tracks, would assist with SKG 1D, Polar Resources 3, which determines the geotechnical characteristics of cold traps. Also, SKG 1D Polar Resources 4, which addresses the physiography and accessibility of cold traps for both robotic and human assets. And SKG 3C2, which evaluates in situ the trafficability of mobile assets. Those data can also provide precursor information for addressing several other SKGs that I list here that include radiation shielding, technologies for the excavation of lunar resources, technologies for transporting those resources, technologies for comminution of that material for ISRU processes, and for modeling the trafficability throughout the lunar surface. So in conclusion, Artemis crew and complementary robotic missions that are scheduled early in the exploration process provide an opportunity to test and calibrate regional assessments of regolith physical properties. Such assessments will reduce the risk associated with future missions and potentially constrain costly requirements needed for the development of surface technologies. Thank you again, Patrick.
Thank you, David. Very good. And so the floor is open for some questions to David about these fantastic possibilities. So do we have questions?
I would have one, if that's okay.
Okay, go ahead.
I was just curious, Dave, what are your thoughts about how much time should be dedicated to soil mechanics experiments during Artemis, for example? Is it like 1% of the time or 2%?
Oh, I think that is a trade study that, first of all, requires analog field studies. We need to determine how long it takes to make a cone penetrometer measurement using the new XEMU spacesuit and enhanced crew capabilities and vane shear device measurements. And so once we have those numbers in analog terrains, then we can see how they might be built into an EVA sequence.
And David, what about, let's say, the final selection between the different sites that you discussed? What kind of a timeline do you have in mind?
Oh, well, the primary mission is likely to be sample collection for sample return. That is going to be the way in which we meet the highest priority science and exploration objectives. And so I envision that type of traverse to pass by these or similar sites and during the EVA implement those cone penetrometer vane shear device measurements. This is basically exactly the same process that was applied during Apollo. These types of physical measurements were made during Apollo in the course of collecting suitable samples to address the highest priority science and exploration priorities, objectives, excuse me.
Okay, thank you. One more question, and then we don't forget, guys, that we have to go to the group photo. But
there's one question in chat by Sarah.
Okay.
If you have the time, and Sarah is interested in whether you're observing a change in bearing capacity when going away from the poles or on the South Pole.
Could you repeat that again, Valentin?
Sorry, yeah, it wasn't very clear. So Sarah asks if there is we observe a change in bearing capacity when you move away from the South Pole towards the equator.
I'm still not sure I understand. So if the question is, are our findings requiring or suggesting or recommending that Artemis not go to the lunar South Pole? Definitely not. In fact, I think our findings show that bearing capacities in the immediate vicinity of the South Pole are not that different than those at Apollo. That said, there are going to be local regions, such as at the base of slopes or on slopes, where bearing capacities will need to be evaluated with some caution.
Yeah, but talking about this bearing capacity changes, as long as we stay close to Shackleton, let's say, what kind of variability do we expect? 10, 20, 25% variation or less?
Oh, there was a 200% variation throughout the mapped area. Yeah, so it can vary quite a lot. But the regions that, to put it another way, there are trafficable, safe bearing capacity routes throughout the region. So there does not appear to be, from our orbital analyses, any impediments to traverses in that region, mindful, of course, of the tremendous topography. I think a lot of people do not appreciate the fact that Shackleton is 4.2 kilometers deep. That's 3 times deeper than the Grand Canyon. So nobody is going from the rim of Shackleton to the floor of Shackleton. I think people also don't understand that the Massif, Malapert, and the one adjacent to it are towering above the lunar surface like Mount Everest on Earth. And so there are going to be topographical barriers to traverses that greatly exceed bearing capacity constraints.
Okay, thank you very much, David. It was very appealing, but I think we have to move now. And